Today we're diving into something really fundamental, mass. We often think of it as this simple, inherent property of stuff, right? But what if that's not the full story? And how could something so seemingly classical be deeply intertwined with one of the weirdest quantum phenomena, entanglement? The idea that particles, no matter how far apart, can be instantly linked. Our mission today is to explore this surprising, kind of nuanced, and deeply context dependent relationship between a particle's mass and its capacity for quantum entanglement. Okay, let's unpack this. We'll start by maybe reshaping your understanding of how mass even rises in the universe. Then we'll get into the ingenious ways entanglement is generated across the entire mass spectrum, of photons to elementary particles and even objects you can almost see. Then we'll grapple with the critical, often destructive role of mass in stripping away quantum coherence. That's through a process called decoherence. And finally, we'll reach the speculative, really cutting-edge frontier where quantum mechanics meets gravity, a place where mass holds the key to some of the universe's deepest secrets.
Yeah, and for you as someone curious, looking for those aha moments in modern physics, understanding this interplay, it offers a unique and powerful lens into the fundamental nature of reality itself. It's really not just about tiny particles. It's about the very fabric of existence and how we understand it.
So let's begin right there, challenging that common perception of mass as just this single intrinsic attribute. Our sources reveal a surprising duality about how mass actually comes about. It's not just one thing, is it? A simple property. How does that work?
Right, it's a profound shift in thinking, really. In modern physics, mass isn't monolithic. It emerges from, well, at least two distinct physical mechanisms. The first, and maybe the most surprising insight, is that for many fundamental particles, their mass is generated by their constant interaction with an invisible field, the Higgs field. It's everywhere.
Okay, the Higgs field. But it's not like drag, right? That's a common misconception.
Exactly, not drag. Think of it more like a stickiness to the very fabric of space. The Higgs field permeates all of spacetime, and even in its vacuum state, it has this constant underlying energy, a kind of universal hum. Particles that interact with this field effectively gain inertia. This interaction provides a restoring effect for their quantum fields, allowing them to support these wave-like ripples with a characteristic resonant frequency. And in quantum field theory, this resonant frequency is directly proportional to the particle's mass.
So the more interaction, the more mass.
Precisely. The stronger a particle sticks to the Higgs field. Its technical term is Yukawa, coupling the greater its mass. This mechanism gives mass to fundamental fermions like quarks and electrons, and also the W and Z bosons, the weak force carriers. But particles that don't interact with the Higgs field, like the photon and the gluon, they lack this stickiness and remain massless.
That's an incredible theoretical picture, but is it just theory? Or, has it been proven?
Oh, it's been definitively proven. The experimental confirmation came, famously with the discovery of the Higgs boson at the Large Hadron Collider, the LHC, back in 2012.
Right, the Higgs boson itself.
Yes, the quantum excitation of the Higgs field itself. Finding it validated this fundamental mechanism. It was a monumental achievement for physics. Now the second origin of mass is completely different. And maybe even more mind-bending. It comes from pure binding energy. This is Einstein's EBHEIS.
EMCS, like energy is mass.
In this context, yes. The most striking example is the proton, which makes up most of the ordinary matter around us. It's made of 3 tiny quarks, but those quarks only account for about 1% of the proton's total mass.
Only 1%, so where's the rest?
The remaining 99% comes from the immense energy of the strong force binding those quarks together. This includes their relativistic kinetic energy and, crucially, the field energy of the massless gluons whipping around inside, mediating the strong force. It's an incredibly complex dynamic internal structure. We actually need powerful computer simulations like Lattice QCD to fully understand it.
Wow. So, okay, we have mass from the Higgs field, you called it intrinsic mass, and then this emergent mass from binding energy, which is essentially pure energy. How does this duality, this difference in where the mass comes from, matter when we talk about quantum behavior or entanglement?
Well, this distinction is really profound. It suggests the origin of a particle's mass might indeed play a role in its quantum behavior. Think about it. A fundamental particle, like an electron, gets its mass entirely from one interaction, the Higgs. Simple, relatively speaking. But a composite particle, like a proton, gets most of its mass from this incredibly complex, boiling cauldron of quarks and gluons constantly interacting.
So it's internally much more complex.
Exactly. That internal complexity means a proton might offer far more pathways for interaction with its environment, and thus potentially more channels for processes like decoherence, which we'll get to, than a simple electron. even if they had similar mass. It just sets a much more nuanced stage.
That sets us up perfectly. Our next big question: how is entanglement actually created? It often feels like this mysterious, almost magical state, but our sources suggest it's actually a natural, maybe even common consequence of quantum interactions.
That's absolutely right. The foundational prerequisite, the starting point for entanglement, is simply interaction between quantum systems. When two or more quantum systems interact in a way where their individual properties like energy, spin, momentum become intertwined, meaning you can no longer describe one particle's state without referring to the others. They can become entangled.
Intertwined. So mathematically, what does that mean?
Mathematically, it means their combined quantum state is non-separable. You can't just write it as particle A is in this state times particle B is in that state. It's one combined state description. This non-separability means you can't describe one particle independently, even if they fly miles apart.
Okay, interaction is key. But what guides these interactions in the real world? Is it just any interaction, or is there something deeper?
Oh, there's definitely something deeper. The central role here belongs to fundamental conservation laws.
Conservation laws, like energy momentum.
Exactly. Conservation of energy, linear momentum, angular momentum, electric charge. These fundamental rules of the universe. When applied in a quantum context, these laws don't just constrain things, they actively necessitate entanglement in many situations. They effectively imprint correlations onto the shared quantum state of the interacting particles.
Can you give an example?
Sure. Take a particle with zero spin that decays into two particles, each with spin 12, like an electron and a positron. Angular momentum conservation demands their total spin must still be zero. The only way to achieve that is if they end up in an entangled singlet state.
Singlet state, meaning?
Meaning their spins are perfectly anti-correlated. If you measure one as spin up, the other is guaranteed to be spin down and vice versa, instantly. No matter how far apart. It's like two sides of a coin that somehow always land opposite, even if you flip them in different cities. Another example is momentum conservation. If the stationary particle decays, its products must fly off in opposite directions with length momenta, so the total momentum remains zero. Their fates are tied. Historically, early experiments used excited calcium atoms. They decayed in steps, emitting two photons whose polarizations were entangled because of angular momentum conservation during the cascade. And even in high-energy physics, things like conserving baryon and lepton numbers ensure correlations that lead to entanglement. So what's fascinating here is entanglement isn't some extra magical property added on top. It's the direct, necessary physical consequence of these fundamental conservation principles playing out within the rules of quantum mechanics.
Okay, so the principles are universal. Conservation laws drive it. But the practical methods for actually making entangled particles must change depending on what you're working with, right? Massless photons versus massive electrons, or even bigger things.
Absolutely. The experimental toolkit changes dramatically as you move up the mass scale.
Let's start with the easiest, perhaps. Massless photons. They seem to be the workhorses in quantum experiments.
They really are. Photons are the experimentalist friend here. They're massless, relatively easy to produce, manipulate, and detect. The most common technique today is called spontaneous parametric down-conversion, SPDC for short.
SPDC, right. How does that work?
Well, you take a high-energy pumped photon and shoot it into a special nonlinear crystal. Inside the crystal, that pumped photon can spontaneously split into a pair of lower-energy photons called the signal and idler. And because of energy and momentum conservation within the crystal, the properties of this pair are strictly correlated.
Correlated how?
Often their polarizations are entangled, or their emission times and energies are linked in an entangled way. This is a very reliable source.
Yeah.
And as I mentioned, atomic cascades were also historically important. An excited atom emits two photons in sequence, and angular momentum conservation links their polarizations.
Okay, that covers photons. Now let's add some mass. What happens when we try to entangle particles with actual substance, like electrons, atoms, or molecules?
This is where things get significantly trickier. The main challenge is shielding them from the environment. Any interaction with the outside world can destroy the delicate entanglement. So you usually need extreme isolation and cooling, often down near absolute zero.
Near absolute zero. Okay, so what are the techniques?
A prime example is trapped ions. You take individual charged atoms, say beryllium-9 ions, you hold them steady using electromagnetic fields like in a tiny trap, and then use lasers to cool them right down to their lowest possible energy state, almost perfectly still.
Laser cooling, got it. Then what?
Then you use precisely timed laser pulses. These lasers can couple the ion's internal electronic states, which act as your quantum bits, or qubits, to their shared quantized vibrational modes in the trap, the way they jiggle together.
Vibrational modes, like phonons.
Exactly, phonons. These shared vibrations act like a quantum bus, allowing you to pass quantum information and create entanglement between ions that might not be directly interacting
The
otherwise.
quantum bus. Cool. What about neutral atoms?
Similar ideas apply. For neutral atoms, or even molecules, researchers use optical tweezers, tightly focused laser beams, to grab and hold them. Then they can use interactions like dipole forces or carefully timed microwave pulses to create entangled states between nearby atoms. There's also a really crucial technique for quantum networking called hybrid atom-photon entanglement.
Hybrid. Atom and photon.
Yes, you entangle the state of a trapped atom, which can act as a stable quantum memory with the polarization or some other property of a photon that it emits. That photon then becomes a flying qubit, carrying the quantum information entangled with a stationary atom. You can send it down an optical fiber.
That's already incredibly complex. But wait, here's where it gets really interesting. Our sources talk about entangling top quarks. These are fundamental particles, yes, but they're incredibly massive, right? Heavier than some whole atoms. How on earth do you entangle those?
Right, this is a truly monumental feat of experimental physics. The top quark is the heavyweight champion of elementary particles, about 173 GeV, heavier than a tungsten atom, like you said. You can't just trap one. They're produced fleetingly in high-energy proton collisions at the LHC.
So produced in pairs.
Yes, top quark-antiquark pairs. And just based on fundamental conservation laws, similar to the spin example earlier, the spins of these newly created top and anti-top quarks should be entangled right from the moment they're created.
Okay, they should be, but how do you check?
That's the monumental challenge. The top quark is incredibly unstable. It decays in about 10 to the minus 25 seconds.
Wow, that's unimaginably fast.
It is far too short for any direct observation or measurement of its spin before it vanishes.
Right.
So physicists at experiments like Alice at CERN had to be ingenious. They couldn't see the top quark spin directly. Instead, they meticulously measured the angular distributions of its decay products, the W bosons and bottom quarks that fly out.
They looked at the debris, essentially.
Exactly. They analyzed the directions and energies of these decay products, and they found correlations between them. Correlations that were stronger, more specific, than anything classical physics or just random chance could explain. This more than classical correlation was the unmistakable fingerprint, the smoking gun, of the underlying quantum entanglement of the parent top quarks that created them.
That's incredible. Inferring entanglement from the decay pattern?
It was a landmark result. It confirmed entanglement persists even at these extreme energy and mass scales for a fundamental particle.
And it gets even bigger. We're not just talking particles now. What about the macro world? Objects you might actually sort of see. Has entanglement really been demonstrated there?
It has, remarkably. Researchers have really pushed the boundaries, successfully entangling what we call mesoscopic objects, sort of in between micro and macro. In one famous experiment, they entangled a tiny, millimeter-sized vibrating membrane. Think like a minuscule drumskin made of trillions of atoms.
Trillions of atoms. Okay.
With a distant cloud of about 1 billion cesium atoms.
1 billion atoms. How? What connected them?
Photons again. Light mediated the entanglement. A laser beam was used. First, it interacted with the atomic cloud, becoming correlated with the collective spin of those billion atoms. Then, that same light beam reflected off the vibrating membrane. This reflection subtly imprinted information about the membrane's physical position, its vibration onto the light. Because the light was already correlated with the atoms, this created a three-way correlation, effectively entangling the membrane's motion with the atomic cloud's spin state, even though they were physically separated.
Wow. Entangling vibration and spin across macroscopic objects using light.
Exactly. The significance is huge. First, it proves entanglement isn't just a weird feature of the subatomic world, it extends much further. And second, these experiments are crucial for developing ultra-sensitive quantum sensors. Imagine improving gravitational wave detectors like LIGO. And also for studying that fundamental fuzzy boundary between the quantum and classical worlds. How does classical behavior emerge from underlying quantum rules? But this raises an important point, doesn't it? As the mass of the system goes up from photons to ions to membranes, the experimental focus shifts. It moves from relatively simple manipulation to this immense challenge of controlling really complex many-body systems, and crucially, protecting them from their ever stronger coupling to the environment. They just interact more.
Right. Which leads us directly to the flip side, entanglement. Its fragility. Decoherence. This is the crux, isn't it? We just don't see cats that are both alive and dead, or, baseballs in two places at once in our everyday lives. Why not? Our sources say mass doesn't directly prevent entanglement, but it makes it incredibly fragile. And that fragility is down to decoherence. So how does that work? What is decoherence?
Yeah, decoherence isn't some mysterious force that just switches off quantumness. It's actually a very physical process, and it's rooted in entanglement itself, ironically.
Entanglement causes the loss of entanglement.
In a way, yes.
Hmm.
Any quantum system, especially a larger one, is never truly isolated. It inevitably interacts, it couples, it becomes entangled with its vast, uncontrolled environment. Think air molecules bumping into it, thermal photons washing over it, even vibrations in the table it's sitting on.
Okay, so it gets tangled up with everything around it.
Precisely. Decoherence happens when the system becomes entangled with this environment. The mechanism is fundamentally about information transfer. If the environment can, even in principle, gain information about the quantum system state, like which path did that particle take, is the cat alive or dead, then the system and environment become linked in one huge, messy, entangled state. Now, when we look only at the original system, because we can't track the trillions of environmental particles, the quantum interference terms, the very signature of superposition and coherence, they effectively average out. They vanish from our perspective.
So the quantumness isn't gone, it's just smeared out.
Exactly. It's delocalized into the combined system plus environment state, which is far too complex for us to observe. The system appears classical to us, even though the underlying quantum evolution is still happening for the whole combined entity.
That's a really clear way to put it. Okay, so how does mass make this process so much more efficient? Why is decoherence so much worse for heavier things?
Mass acts as a powerful amplifier for decoherence for a couple of key reasons. First, just interaction strength. A larger, more massive object simply presents a bigger target. It's physically larger, often has more constituent particles, more ways to interact, so it will scatter more environmental particles, photons, gas molecules per unit time. And each one of those scattering events can potentially carry away which state information, revealing the system's quantum state to the environment and thus causing decoherence.
More bumps, more information leakage. Makes sense.
Right. And second, there's a more subtle quantum aspect related to something called the thermal de Broglie wavelength. This wavelength, leb-b, is given by Planck's constant divided by the square root of 2 times mass times Boltzmann's constant times temperature. The key thing is it's inversely proportional to the square root of mass.
Okay, so bigger mass means tiny wavelength.
Incredibly tiny. For a macroscopic object, like just a 1-gram speck of dust at room temperature, this wavelength is minuscule, something like 10 to the minus 23 meters. Smaller than a proton. Decoherence becomes overwhelmingly efficient when the physical separation of a quantum superposition, like trying to have that speck in 2 places at once, is much larger than this tiny de Broglie wavelength. The environment can very easily distinguish between the locations because they're so far apart compared to this quantum fuzziness scale. That's why we just don't see macroscopic quantum effects in daily life. The environment finds out the state almost instantly. So what's fascinating here is this fundamental duality. The very phenomena we want to harness good entanglement between our quantum bits uses the same mechanism interaction that leads to its destruction through bad entanglement with the environment. And mass is the critical parameter that just cranks up the volume on that coupling to the environment, making useful entanglement incredibly fragile and short-lived for bigger things.
Wow. So the challenge of quantum science, especially with more massive objects, really boils down to this engineering problem. How do you encourage the interactions you want while minimizing, almost perfectly, the leakage of information and thus the spread of unwanted entanglement into the environment? It's a constant battle against nature, in a way.
That's a great way to frame it.
Okay, now let's push to the absolute cutting edge, where mass and entanglement meet the most mysterious force we know, gravity. Our source material hints at this really provocative idea. Gravity might have a dual role, potentially acting as both a creator and a destroyer of entanglement. That sounds almost contradictory. How could that be?
It does sound contradictory, and this is truly the frontier where theory and experiment are just beginning to explore. The pivotal question is fundamental. Is gravity purely classical, as described by Einstein's general relativity, or does it have underlying quantum properties like the other forces?
Does gravity have gravitons, essentially?
That's one way to think about it, yes. Does the gravitational field itself have quantum degrees of freedom? A class of proposed experiments, often linked to ideas from Bose, Marletto, and Vedral, aims to test this using something called gravitationally induced entanglement, or GIE.
GIE. Okay, what's the idea?
The core concept is conceptually simple but experimentally mind-boggling. You take two massive particles, maybe tiny diamonds or something similar. You prepare each one in a spatial superposition, so each exists in two locations simultaneously, quantum mechanically. Then you hold these two superpositions close enough that they interact only via their mutual gravitational attraction. You shield everything else.
Only gravity connecting them.
Right. Then, after some time, you measure them. The core logic is this. If you find that the final states of these two masses are entangled with each other, then the gravitational field itself must have acted as a quantum mediator, a quantum channel, because a purely classical field, according to quantum information theory, cannot create entanglement between two initially separate quantum systems.
So finding entanglement would imply gravity is quantum.
That's the profound implication. The proposed mechanism involves tiny quantum phase shifts accumulating differently for different parts of the superpositions due to the gravitational potential between them. But the challenges are just immense. You need to create and maintain macroscopic quantum superposition for potentially long times, achieve sufficient gravitational interaction, which is incredibly weak, and perfectly shield from all other environmental decoherent sources, which are vastly stronger.
Seems almost impossible. Are people actually trying this?
Oh yes. There are active experimental proposals and efforts using things like optomechanical oscillators, tiny vibrating mirrors, or sophisticated atom interferometers. It's a major goal in experimental physics right now.
Okay, so gravity might create entanglement, proving its quantum nature. But you hinted at the other side of the coin. Could gravity also destroy entanglement, act as a source of decoherence?
That's the converse idea, often called gravitational decoherence, or GD. And it makes sense why gravity is a prime suspect for a fundamental decoherence mechanism.
Why is that?
Because it's universal, it affects everything with mass or energy. And crucially, unlike electromagnetic noise, you can't shield from gravity. It permeates everything. So if a particle is in a superposition of locations, its own gravitational field is, in a sense, also in a superposition. And that superposed field is interacting with the rest of the universe, potentially leaking information.
So gravity itself could be the environment.
Exactly. There are broadly two types of models exploring this. First, you have phenomenological collapse models, like those pioneered by Diossi and Penrose. These models propose a fundamental conflict between quantum mechanics and general relativity, suggesting that gravity causes a spontaneous collapse of the wave function for massive objects. The rate of collapse would be proportional to the object's gravitational self-energy. These actually modify standard quantum mechanics.
A modification of QM itself. Okay, what's the other type?
The other type operates within standard frameworks, often called environment-based models, linked to work by people like Anastopoulos, Blumenkow, and Hu. They suggest decoherence arises more conventionally, from entanglement with ambient fluctuations in the gravitational field itself, maybe virtual gravitons, or even primordial gravitational waves left over from the Big Bang. It's analogous to how a bath of thermal photons causes decoherence for charged particles.
And in both types of models, mass is key.
Absolutely. In all such models, the predicted decoherence effect is strongly mass-dependent. It becomes much more significant for more massive objects in superposition. And for systems with many particles, like a large molecule, even the gravitational pull between different parts of the molecule could potentially act as an internal environmental source, causing entanglement to degrade. The challenge, again, is designing experiments sensitive enough to detect these incredibly subtle gravitational decoherence effects, distinguishing them from all the mundane environmental noise. So if we try to connect this to the bigger picture, we see this profound potential duality in gravity's role. The very same quantum degrees of freedom of the gravitational field, the things that might mediate entanglement in GIE experiments, are also proposed to act as a universal environmental bath that could destroy entanglement in GD models.
Like how the electromagnetic field gives us lasers, but also noisy thermal radiation?
Precisely analogous. The EM field can be a channel for coherent quantum information, lasers, or a source of decoherence, blackbody radiation. Gravity might be similar. Resolving this duality is gravity fundamentally a quantum channel, a decohering environment, or perhaps both, is a central goal of experimental quantum gravity. Observing GAE would be groundbreaking, characterizing gravity as quantum. Meanwhile, experiments searching for GD, even if they only set limits, constrain gravity's nature as a potential source of decoherence. So studying mass and entanglement, especially at larger scales, isn't just about quantum technology. It's become a direct experimental probe into the fundamental nature of spacetime itself.
Okay, so bringing it all together then, we've covered a huge amount of ground, but it really seems to boil down to maybe three main ways mass influences entanglement. Is that fair?
I think so. Let's recap.
First, mass dictates the underlying interactions, right? Whether it's the Higgs mechanism giving intrinsic mass, or binding energy creating emergent mass, or just the conservation laws applied to massive particles. These provide the very mechanisms for generating entanglement in the first place.
Exactly. The origin and value of mass shapes the interactions available.
Second, mass acts as this potent amplifier for decoherence. It makes systems interact more strongly with their environment, making it the critical factor in the battle to preserve these fragile quantum states, especially as things get bigger.
Definitely. Mass is the key parameter governing the rate of environment-induced entanglement or decoherence.
And finally, at the ultimate frontier, this intrinsic connection between mass and gravity puts it right at the center of the quest to understand the quantum nature of spacetime. Gravity, linked inextricably to mass, is hypothesized to act as both a creator and a destroyer of entanglement.
That captures the cutting edge perfectly. Mass is the handle we have on potentially probing quantum gravity effects through entanglement. Of course, the path ahead is, well, it's incredibly challenging, both experimentally and theoretically. Just the practical realization of those GIE experiments maintaining macroscopic quantum superpositions long enough for gravity to act while shielding them perfectly. It's a monumental task.
And telling the difference between all the proposed decoherence models.
Right? Designing experiments sensitive enough to distinguish between, say, fundamental collapse models and environment-based gravitational decoherence. That's extremely difficult. And the overarching goal of a truly unified theoretical framework, a quantum theory of gravity, that remains a long-term horizon.
But what an exciting horizon it is. It feels like mass, far from being just a simple classical property or even just an impediment to the quantum world, it's actually become the very lever, the tool physicists are hoping to use to pry open the deepest secrets of the universe, the quantum nature of gravity itself.
That's beautifully put. The successful entanglement of ever more massive objects isn't just a series of technical milestones. Each step represents crucial progress on the path toward understanding that quantum to classical transition and potentially forging that unified theory of quantum gravity. So for you listening, what stands out most about how profound and maybe how strange that journey is?